Okay, welcome to part 4 of the 310 videos. Let's go ahead and talk about the rules for inverse trig derivatives after we've kind of taken a look at how to derive them. So I'm going to do the first few that we did. I'm going to just write down the ones that we had. We had dy. Sorry, hold on. Let me do this. If we have d dx of sine inverse of x, then that's going to give us 1 over the square root of 1 minus x squared. Okay, if we took the derivative with respect to x of cosine inverse of x, then we got negative 1 over the square root of 1 minus x squared. Okay, so remember that these were very similar. It's just that the derivative of our cofunction of sine is just opposite. Okay, so if we take a look at d dx of tangent inverse of x, then that's just going to give us 1 over 1 plus x squared. Okay, so those are the ones that we derived. Let's take a look at the derivative with respect to x of cotangent inverse of x, and that's just going to give us negative 1 over 1 plus x squared. Okay, so it follows that same pattern of the derivative of cofunctions are negative. Okay. Now, the one that I didn't derive is secant inverse, and that one's pretty difficult to explain. So I'm just going to give you the rule, and we're just going to use the rule. But that's d dx of secant inverse of x, and that's going to be 1 over the absolute value of x times the square root of x squared minus 1. Okay, so that's that. And so you can, given that derivative, you can say that d dx of cosecant inverse of x is just the opposite of that. So it's negative 1 over the absolute value of x times the square root of x squared minus 1. Okay, now these are just the regular inverse trig derivatives. I do want to talk about the chain rule in here as well. So I'm going to do that here. I'm going to write chain rule. Dang it. Okay, chain rule. Okay, and someone maybe say that this is off the chain. Okay, so let's take d dx of, say, sine inverse of some function u, then that's just going to give me u prime over the square root of 1 minus u squared. Okay, so the same thing that we've been doing for a while. Okay, if I take d dx of, say, cosine inverse of some function u, then that's going to give me, I'm going to move this over, that's going to give me negative u prime over the square root of 1 minus u squared. Okay, so let's take a look now at, say, the derivative with respect. And it's just going to be d dx of, say, tangent inverse of some function u. Okay, and that's going to be u prime over 1 plus u squared. Okay, and then we're going to do d dx of cotangent inverse of u, and that's going to give us negative u prime over 1 plus u squared. Okay, now let's do secant and cosecant. So if I do d dx of, say, cosecant, or not cosecant, let's do secant. Say secant inverse of some function u, then that's going to give us u prime over the absolute value of u times the square root of u squared minus 1. Okay, and if I take the derivative with respect to x of, say, cosecant inverse of some function u, then that's going to give us negative u prime over the absolute value of u times the square root of u squared minus 1. Okay, so those are the rules that we have. Now let's apply those rules and talk about what we've got in some of these practice problems. So the first thing I'm going to do is take a look at number 24 here. I realize that my function is an inverse trig function, and I have my ratio of sides is itself a function. Okay, so I have to use the chain rule here. So I'm going to call this part u. So let u equal 1 minus t. Okay, so I'm going to rewrite this as y equals sine inverse of u. Okay, and from our rules we know that y prime, which is the same thing as dy dx, is equal to u prime over the square root of 1 minus u squared. Okay, so in order to find that derivative, I need to find u prime. Okay, so u prime is equal to negative 1. And so then my derivative y prime, which is the same thing as dy dx, is equal to negative 1 over the square root of 1 minus the quantity, 1 minus t quantity squared. Okay, so that's that. Pretty simple. Just follow the rules. Okay, let's take a look at the next one, 34. And so same thing again, tangent inverse, it's of my ratio is a function, okay? And so I'm going to have that be my u. So I'm going to let u equal the natural log of x, okay? And so then I'm going to rewrite this as y equals tangent inverse of u. So if I found y prime, my derivative, which is the same thing as dy dx, then my rule is u prime over 1 plus u squared. Okay, so I'm going to go ahead and plug in my values. I do need to find my derivative of u, so u prime is just 1 over x. Okay, so y prime, which is dy dx, okay, is equal to u prime, which is 1 over x divided by 1 plus the quantity ln of x squared. Okay, and that's my derivative. We could simplify that, but I'm not going to do that. Ain't nobody got time for that. So let's take a look. Okay, we got one more to do. So cosine inverse of e to the negative t. In this one, same thing, guys. We got to use chain rule. All right, so this is my input. This is my u. That's my ratio of sides. So I'm going to let u equal e to the negative t. Okay, so let me find my derivative of that. That's u prime is going to be negative e to the negative t using the chain rule. Okay, so I'm going to rewrite this as y equals cosine inverse of u. Okay, and my derivative, okay, y prime, which is dy dx, okay, is equal to negative u prime over the square root of 1 minus u squared. Okay, so I'm going to go ahead and plug my values in. So we get y prime is equal to dy dx, and that's negative e to the negative t. A lot of negatives. Okay, I'm pretty positive person, but you know, just got to deal with our negatives here. And then it's over the square root of 1 minus the quantity, e to the negative t quantity squared. Okay, and we could simplify that just a little bit and say that's positive e to the negative t divided by the square root of 1 minus the square quantity e to the negative t squared. Okay, so that's my derivative of that. And so I hope you enjoyed this video, guys. We've got some homework. Okay, and that's always fun. Okay, so go ahead and take a look at this homework. It's not too bad. Solutions are online, so I hope you have enjoyed this video, and we will see you on the next time. Okay, bye.